Hello, Accelerated Chemistry students. This is Miss Crystal Foley, and this is your Chapter 5, Section 2 video notes all over electron arrangement in atoms. So the ways in which electrons are arranged in various orbitals around the nucleus of atoms are called electron configurations. And there are 3 rules that we need to follow in order to do this correctly: the Aufbau principle, the Pauli exclusion principle, and Hund's rule. And these will all tell you how to find an electron configuration of an atom. So let's start with the Aufbau principle. So according to the Aufbau principle, electrons occupy the orbitals of lowest energy first. So in this Aufbau diagram, each box is going to represent an atomic orbital. And you're going to fill the ones on the bottom first, and then you're going to fill the one moving up. Next, the Aufbau diagram shows the relative energy levels of the various atomic orbitals. Orbitals of greater energy are higher up on the diagram. And then finally, the range of energy levels within a principal energy level can overlap the energy levels of another principal level. That sounds a little confusing, but if you were to think about it, it will make sense. The Aufbau principle allows for orbitals to be very close in energy. Now let's talk about Pauli exclusion principle. According to the Pauli exclusion principle, an atomic orbital may describe at most 2 electrons. So we know that electrons are negative, so that to occupy the same orbital, the electrons must have opposite spins. So what does that mean? That means that the spin is a quantum mechanical property of electrons and may be thought of as clockwise or counterclockwise. So a vertical arrow indicates an electron and its direction or spin. So if it's up, it's positive 1/2, and if it's down, it's negative 1/2. So an orbital containing paired electrons is written as a box like this with one arrow facing up and the other one facing down. So let's talk about Hund's rule. According to Hund's rule, electrons occupy orbitals of the same energy in a way that makes the number of electrons with the same spin direction as large as possible. So what does that mean? That means if 3 electrons could occupy 3 orbitals of equal energy as follows. So basically all this is saying is that you're going to fill in your orbitals in your diagram with all arrows up first if they're in the same sublevel, and then you pair them up. So a convenient shorthand method for showing the electron configuration of an atom involves writing the energy level and the symbol for the sublevel or the shape of the orbital occupied by the electron. And then you indicate the number of electrons occupying the sublevel with a superscript or an exponent. So let's look at hydrogen. So for hydrogen, we have 1 electron. So if we were going to fill in the Aufbau diagram, we would start at the bottom, so the 1s, we'd put 1 electron in there. And so if we were to write the electron configuration for hydrogen, we would say that in the first energy level, in the s orbital, there is 1 electron. Now, the sum of the superscripts in an electron configuration is going to be equal to the number of electrons in the atom that we're talking about. So we only have 1 superscript, 1 exponent, and it is a 1. So 1 plus nothing else is going to be 1, and that's how many electrons we have for hydrogen. So let's look for oxygen. For oxygen, we have 8 electrons. How do we know how many electrons we have again? We look at our periodic table. If you don't have it out, I would pause the video and grab it. And you're going to look for the atomic number. The atomic number, remember, tells us the number of protons. And for right now, it also is going to tell us the number of electrons because all of these elements are neutral. So if we add our electrons into our Aufbau diagram, we're going to go up and then down because remember they need to be opposite spin. 2s, we're going to go 1 up, 1 down. And then the 2p, we're going to go 1 up, 1 up, 1 up. So let's check. We have 2, 4, 5, 6, 7. Up, we need 1 more. And he's going to face down in the first orbital. All right, so if we were to write the electron configuration based on our picture, we would say that we have 2 electrons in the 1s orbital, 2 electrons in the 2s orbital, and 4 electrons in the 2p orbital. And that's what we write. 1s2, 2s2, 2p4. And remember, the sum of the superscripts or the exponents in the electron configuration is the number of electrons in the atom that we're talking about. So let's look at a sample problem, 5.1 from your textbook, writing electron configuration. So the atomic number of phosphorus is 15. So we're going to write the electron configuration of a phosphorus atom. So first, we're going to analyze. We're going to identify the relevant concepts that we need in order to do this problem. We know that phosphorus has 15 electrons. There is a maximum of 2 electrons per orbital, and electrons do not pair up with an energy sublevel until each orbital already has 1 electron. So remember, when writing electron configurations, the sublevels within the same principal energy level are going to be written together. So let's look at this. So let's solve. So we're going to use the off-bog diagram to place electrons in the lowest energy 1s first. So we have to put 2 in there. So remember, we started off with 15 and now we have to place 13 more. So in order to place 13 more, we got to continue filling. So we have 2, 3, 4, 5, 6, 7. Make sure you're paying attention on how I'm filling these in. So we're at 7, 8, 9, 10, 11, 12, 13, 14, 15. So we've placed all of our electrons. So now if I were to write the electron configuration for this, I would say 1s2, because I have 2 electrons in the 1s orbital, 2s2, because I have 2 electrons in the second s orbital. Then I would go 2p6, because I have 6 electrons in the 2p orbitals, 3s2, because I have 2 electrons in the 3s orbital, and then 3p6, or 3p3, excuse me, because I only have 3 electrons, not 6. I only have 3 electrons in the 3p orbital. And if we were to sum up our superscripts, we have 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 3 is 15. I have all of my electrons that I was looking to place all in the right spots. Now, there are exceptions to the electron configuration. So we have exceptional electron configurations. So you can obtain correct electron configurations for elements up to vanadium, which is atomic number 23, by following the off-bog diagram for orbital filling. However, when you get to places like chromium and copper, you would normally write their configurations like this. However, this is not good. And the reason this is not good is because we need to write their configurations like this. And that's because these arrangements give chromium a half-filled D sublevel, and they give copper a filled D sublevel. So basically what we did is we promoted the one of the electrons from the 4s orbital to the D. So basically one of these went and made this 3d5 instead of being 3d4, and this one made it 3d10 instead of 3d9. That will allow for the energy to be at the lowest, and that's what makes our electrons happy. So, some actual electron configurations differ from those assigned using the off-bog principle because although half-filled sublevels are not as stable as filled, they are more stable than other configurations that the electrons can have. It's not that bad. We're going to practice a lot over the next couple of days dealing with electron configurations. So as always, this concludes the end of your Chapter 5, Section 2 notes over electron configurations, and all the information on these Google slides has been acquired and adapted from Pearson Chem's 2012 edition of the Textbook Resources CD and pearsonchem.com. Thank you so much.